We are going to look at each of these questions. Now, Q1 through Q5 are all targeted toward a specific idea. First question is use substitution, the second integration by parts, the third partial fraction decomposition, the fourth improper integration, and our fifth question is based again on a substitution of some kind. So let's take a look at our first example. So here, when looking at this example, when we see it, we see 3x tan x squared integral du, dx. And when I see this, I think, okay, this is a function outside and a function inside. Internally, my head's going, okay, u equals x squared. I'm thinking this inside piece here, that is x squared. That's my u. So du by dx equals 2x, 1 over 2x du by dx equals 1, which I can introduce. So this equals 3x over 2x tan x squared du by dx, which equals 3 over 2 integral tan u du by dx. Now here I've got tan of u, which we don't have any direct rule, but we might see this and we go, okay, what do I do? Well, what we need to do here is we need to recognize that this is 3 over 2 sine of u over cos of u du by dx. And now I'm going to let v equal cos of u dv by dt equals minus sine u, or 1 over minus sine u dv by du. Sorry, this should be dv by du equals 1. So this equals 3 over 2, the integral of sine u over minus sine of u, 1 over cos of u dv by du by dx, which equals minus 3 over 2 integral of 1 over u dv by du by dx. Now what I need to do is I need to integrate this, and sorry, this is 1 over v. I need to integrate this with respect to v and then substitute back for u and substitute back for x. So this equals minus 3 over 2 ln absolute v plus c. Now, v is going to be cos squared, or cos of u. So this equals minus 3 over 2 ln absolute cos of u plus c. And now u equals x squared, so I need to substitute that back in, giving you minus 3 over 2 ln absolute cos of x squared plus c. Okay. So let's remove what we've done so we can do the next problem. Just going to erase that. And now we're going to be looking at the integral of secant squared x tan of x dx. Now this one's interesting because I could either say tan is my u, or I could say secant is my u. And it's not quite clear which one is correct, which one's going to be the one that's the one I would like. Turns out in this case, both work. But whenever we have something with secant to a power paired with tan, we've got to kind of guess one of them, see if it works, and then if it doesn't, try the other. So I claim that both work, and I'm going to show you that both would work. So U equals, we're going to start with secant x. Because U equals secant x, du by dx equals secant x tan x, or 1 over secant x tan x. Du by dx equals 1. Introducing this in, we get the integral of secant squared x tan x divided by secant x tan x du by dx dx. And this equals the integral of secant x du by dx dx, which equals the integral of u du by dx dx, which equals u squared plus u squared over 2 plus c, which equals secant squared x over 2 plus c, which is one of our solutions. Now, if we instead, let's look at this expression and look at the integral of secant squared x tan x dx, and we let u equal tan x, then du by dx equals secant squared x, or 1 over secant squared x du by dx equals 1. Introducing this in, we get secant squared x over secant squared x tan x du by dx dx, which equals the integral of u du by dx dx, which equals u squared over 2 plus c, which equals tan squared x over 2 plus c. Now, secant squared x over 2 plus c and tan squared x over 2 plus c, but tan squared and secant squared aren't equal to each other. Well, why does this work? Well, we have that tan squared x plus 1 equals secant squared x. Because this is true, this here is equal to tan squared x plus 1 over 2 plus c, which equals tan squared x over 2 plus 1/2 plus c. And this 1/2 plus c is just another constant. So this is, we can replace with c, which is what I have down here. So both are valid. Finally, we have our last example for question 1, which is the integral of x squared 1 plus x to the 1/5 dx. And to solve this, we use substitution to move the ugly outside of the root. So what do I mean by move the ugly outside of the root? I mean, take this x plus 1 and move it outside my root by letting u equal 1 plus x. U by dx equals 1. So I get the integral of x squared 1 plus x to the 1/5 du by dx dx. And you might ask yourself, why does this help? Well, here, this implies that x equals u minus 1, which gives me, to complete the substitution, I need to replace x with u minus 1. So it's the integral of u minus 1 squared u to the 1/5 du by dx dx. Now I'm going to expand this u minus 1 squared to give me u squared minus 2u plus 1 all times u to the 1/5. du by dx, dx. Expanding this u to the 1/5, I'm able to distribute this over. So this gives me the integral of u to the 11/5 minus 2u to the 6/5 plus u to the 1/5 du by dx, dx. For each of these, I go up a power over power. So it's u to the 16/5 over 16/5 minus 2u to the 11/5 over 11/5 plus u to the 6/5 over 6/5 plus c. Substituting back and making the fractions look nice gives me 5 over 16 x plus 1 to the 16/5 minus 10 over 11 x plus 1 to the 11/5 plus 5 over 6 x plus 1 to the 6/5 plus c. And we have our solution.